Playing pre-recorded sounds in Max is as easy as dragging a sound in a picture window. This can be done from the Audio tab in the toolbar. Here, all sounds are listed that are in the search path of the application. The help file of this object shows that its name is playlist. A playlist object connects directly to DAC. There is an option to loop the playback of the sound. Another sound can be dragged onto the object, which will be added to the playlist. Also, dragging a sound from a folder into a patch creates a playlist object. A playlist is good for parties, but if the aim is to use the sound as a material from which to create something new, a different approach is required. That approach is buffered sound. A buffer object requires a name and optionally can refer to a sound file with a second argument. A double click on the object shows its content. A new file can be loaded with the replace message. The content of a buffer can be accessed by a number of objects. The first object we will take a closer look at is called play. The argument is the name of the buffer that the object refers to. Play can play the sound with a simple toggle. By setting the loop attribute to the value 1, play will activate its loop mode. Such attributes can be set externally as well, using the attr_ui object, a user interface for attributes. The shortcut is the letter A. The attr_ui allows changing values of attributes without having to type them into the object. In the previous example, a mono file named Cherokee was used. Here, drum loop is loaded into a buffer, which is a stereo sound file. If looping sounds is the objective, groove is a good candidate. A second argument sets the number of output channels, and the loop attribute is enabled. The playback of sound is activated by providing a value for sample playback increment. This value needs to be a signal. The sig object creates a static signal. A number box provides other values for speed. Negative values lead to playing backwards. Additional number boxes set the start point and end point of the loop in terms of milliseconds. In the Audio tab of objects, we find a waveform object. Like any object that refers to buffers, a name must be set. This can be done in the inspector, which is opened in the toolbar on the right. Another option is to open the inspector in a separate window. Make sure All is selected in the right top corner in order to have access to all characteristics that can be changed. When we scroll down a bit, we see an entry for the buffer object name that the waveform will refer to. The click mode is set to loop. The waveform object now displays the content of the buffer and it responds to mouse interaction. Dragging upwards extends the selected loop. Dragging left or right moves the selection around. The start and end points of the selected loop are produced from the third and fourth outlet. The object now becomes a controller for the groove object. Playing a chunk of sound, as we did with groove, can also be achieved with the play object. When we take a look at the help file, we see the start message specified. The start message takes up to 3 millisecond values, from where to play, until where to play, and how long it takes to get there. The distance between the start 300 and the end 900 is 600 milliseconds. If we wish to interact with one of these values, we can introduce a variable argument with the $sign notation. $1 means that from what arrives at the input, the first or only value is taken and inserted in its place. Let's test this by printing into the max window. The third value is 600, which was produced at the inlet. The number box thus represents the duration value. Values higher than 600 lead to lower pitched sounds. Lower values produce higher pitches. The same principle can also be applied to the second value, the endpoint. Now the opposite is true. Higher values lead to higher pitches and lower values to lower pitches. If the end value is before the start, the sound plays reversed. Interacting with two values is possible as well. In this case, two $sign placeholders need to be used. This requires a list to be produced at the inlet. The join object will join together multiple values into a single list. A relationship between duration and endpoint is created by adding the start point to the duration. In other words, the endpoint is the start point plus duration. The result is that regardless which duration we choose, playback is always at original speed. Let's develop this principle a little further. The duration can become the result of a random choice. A trigger to random 300 produces 1 out of 300 possible options. The lowest is always 0, which implies that the highest value possible will be 299. A duration of 0 is undesirable, therefore 10 is added to the random range. We will then expect duration values from 10 to 309. The play object produces a trigger from the right outlet when it is done playing. This trigger can be used for a next random value. In order to be able to stop the process, a pause message can be added. When the end value is multiplied with a factor, the chunk becomes larger when the factor is greater than 1 and shorter when smaller than 1. In the second example, we saw that changing the endpoint equally changes the pitch. Creating a different starting point requires two adjustments: the argument of plus and the first value of the start message. If we want to interact with it, a third $sign can be used. The join object requires an additional inlet. This number box now sets the starting position. In order to have a clearer interaction, The waveform object can be used again. It is fine to type the name in an object box, which gives the option to specify the attribute for buffer name. Again, in the inspector, click mode is set to loop. The starting position now can be produced by scrolling through the waveform. We have seen how the start message using 3 values reproduces a chunk of audio from a buffer. Instead of using this built-in method, the play object can also be driven by a signal. The line object provides such a signal. The message is a set of pairs of destination values and durations. Go to 300 in 0 milliseconds and then move to 900 in 600 milliseconds. Such a signal-driven approach can be applied to another object that relates to buffers, wave. The logic of wave is slightly different and the message needs to be adjusted. Go to 0 in 0, move to 1 in 600. This 0 to 1 transition relates to begin and end points that can be specified through the second and third inlet. A $sign notation again creates the option to interact with the duration value. This value will be produced from the f object, which stores a float value. Another value represents the starting point. We have seen that the endpoint is the duration added to the starting point. The line object, like play, triggers from the right outlet when it reaches the destination. This works fine, but it sounds somewhat rough. Let's make a recording to verify what is going on. The second channel clearly shows the 0 to 1 transition, something that resembles the phasor output that we have seen in a previous episode. Where one chunk ends and a new one starts, there is a clear discontinuity in the signal. This is what creates the pops and clicks. There is a method to smoothen this by creating a short fade-in at the start and fade-out at the end of a chunk, a so-called envelope. The up-down object does that. 2 attributes define fade durations in milliseconds. The object is phase-driven, so the line signal can directly be used for the input. And the output represents a control signal that can be applied to the output of wave, using a multiplication. In order to clarify the logic, let's make a recording of 4 tracks: the phase signal, the envelope, the signal before, and the signal after applying the envelope. That sounds much better. The recording clearly shows the fades on the second channel and how the discontinuity disappears on the fourth channel. Finally, it would be great to interact with the start and duration values other than dragging values in a number box. Max provides for a user interface object with the name picked slider. The default version of this object creates a two-dimensional slider. The horizontal and vertical output values default to a 0 to 127 range. These ranges can be mapped in order to create functional values for the two parameters that we want to control. As a start, the vertical value from the right outlet will be divided by 127 to create a 0 to 1 range. Multiplying this to itself, effectively raising it to the power of 2, creates a curved range with greater precision at the low end. A multiplication with 200 creates a curved range from 0 to 200. The horizontal value will be mapped to position in the buffer. It would be good to know the duration of the sound in the buffer. The info object can provide this information. The third outlet from the right produces a millisecond value that can be used for mapping an input range from 0 to 127 to an output range that represents the size of the buffer. In addition to using pre-recorded sounds, it is possible to record live input into a buffer. An empty buffer is created, now with a different second argument that sets the size in milliseconds. A record object can be set to refer to that buffer, and input from the ADC, or analog to digital converter, feeds into the recording. A toggle is used to start and end the recording. A waveform object helps to verify what is going on. In pure data, sound is stored in a table using the array object. Like in Max, it will be referred to by a given name. The easiest way to load a sound into the array is to point to a sound file with the OpenPanel object that will produce a path to the file. This path will become the variable in a read message for the soundfiler object. The resize flag is invoked and the name of the buffer is provided as a reference. The soundfiler object generates various information about the loaded sound file, including the size in samples and the sample rate at which it was recorded. The object to read sounds from the array is called tapread4 with 4-point interpolation. The line object will drive the tapread. This message can be understood as jump to 0, then move to the sample 44,100 in 1 second. The line object does not have a write outlet, so it does not produce a trigger when it is ready. Instead, a metronome could be used to create a clock, which will choose a random duration. This millisecond value divided by 1000 and multiplied with the sample rate of the sound file will produce an endpoint for line, which is packed in a list with the duration. An offset is easily created by adding a value to the output of line, again applying the same conversion from milliseconds to samples. A 0 to 1 transition as the basis of reading a chunk of sound, just like the wave object in Max, is also possible. In this case, we will have to multiply with the duration and add a starting point. Duration and start will again be stored in f objects from which they are produced by a metronome. Similar conversions from milliseconds need to be applied to both. Applying a window in PD is good practice as well, but there is no object for that. However, we can apply a bit of math. This parabolic function produces something that looks like a window. The square root changes its shape. In pure data, the output of the line object can be considered x in the parabolic function. The rest is straightforward math. Finally, pitch can be changed with a multiplication factor applied to duration. In pure data, recording into the array is provided through the tapWrite object.